and he'll be talking about achromatic meta-optics for microwaves and millimetre waves. So thanks, David.
Thank you, Anne. So Newton's presentation was timely because I think it's already given you some idea of what metasurfaces are. But whereas he was mostly interested in nonlinear effects, I'm going to be sticking to purely linear effects. Now, the work I'm going to be presenting here is primarily done by my former PhD student, Ashif Fatnan, who's now in doing a postdoc in Japan. So metasurfaces in optics, there's a strong interest in replacing bulky devices with some kind of thin film fabricated structure. And in particular, if you have a metasurface where all elements are no longer identical, then you can do things like focus a beam, and you can do that in a much smaller space than the equivalent lens that would perform the same function, say with a bulk dielectric. But the price you pay for that more compact design is that your bandwidth suffers. And so the earliest metasurface designs were really created for a single frequency, and then performance was seen to degrade pretty quickly away from that design frequency. However, there's been a lot of interest in creating various broadband or achromatic metasurfaces, where there's still some trade-off, but you have some non-negligible operating bandwidth for your structure. And of course, a lot of this work has been, as I said, at optics. Our interest here is actually pushing this down to lower microwave and millimetre wave frequencies, where there are applications in, for example, 5G communications or even the subsequent 6G communications, things like automotive radar. And at this frequency range, thickness matters, right? Because, here, these structures, although they're thin, they're of the order of a wavelength. All right. Now, if that's sort of micron or submicron, it doesn't matter too much. But when we move to millimetre or even centimetre wavelengths, that's actually very thick and a bit impractical for fabrication. So this conventional dielectric structures aren't so suitable at lower frequencies. There are some other approaches based on geometric phase that I won't get into. I'll just note that there are some efficiency issues here, and they only really work for circular polarizations, which aren't typically used in the applications we're interested in. But there are other approaches based on long-standing ideas of frequency selective surfaces where circuit-based filter synthesis techniques are applied, and they can give a good performance, at least in theory, but you can end up with a very large number of layers. And also you can find that the thickness of the layers themselves becomes one of the design parameters. Whereas in practice, if we create some printed circuit board, we just like to be able to use the available thickness and optimize only our metallic structure. And so at the frequencies we're interested in, the most common geometry consists of 3 metallic layers. So that's sort of what you see here. May not be clear, but 3 patterned metal layers separated by dielectrics in between, very practical for printed circuit fabrication. They can create what's known as a Huygens metasurface, which effectively just means that your impedance matched to the incoming wavefronts, and so you can refract it without significant reflection back in the incident direction. If we prefer to create a reflective structure, it's even simple. We require only one ground plane and one pattern metallic layer, again, separated by a dielectric. Now, for such designs, all right, circuit-based synthesis approaches, for example, explained in this work, have been very successful. Here, each metal layer is treated as a shunt impedance because they're quite thin, whereas the dielectric layers are replaced by a transmission line. Of course, a transmission line is just kind of equivalent to the Fresnel equations for that dielectric slab. And such approaches have been proven, but only really for narrowband designs. So what we are doing is we're taking these synthesis approaches and making them broadband. And by broadband, I mean you can get full diffraction efficiency over a wide bandwidth, but we also want to make them achromatic. What's the distinction? In achromatic designs, we don't just maintain full efficiency, but we also keep a constant refraction angle, or for a lens, a constant focal length over the operating bandwidth. And so here I'm showing an example as a function of frequency. What's plotted here is the phase response of different elements, so different unit cells within a metasurface. So if we look at first at the conventional narrowband design, right, this dashed line would give the desired phase response, and we see that we only match that at a particular frequency. So these broadband designs really are just about doing a first order correction, all right, where we match to both the desired group phase delay, but also the group delay. So that's effectively matching that phase slope. All right, and we can do this by fitting that desired response to a simple LC equivalent circuit that's shown here. Then just by numerical simulation with a tool such as CST Microwave Studio, we can turn that, realize that equivalent circuit with some kind of patterned metallic layer. All right, here's just a simple dog bone structure, which is effectively a dipole. We've also shown that for some layers or some particular elements are better matched not by a series equivalent circuit, but by a parallel equivalent circuit. And that corresponds to a metasurface where the metallic layer is continuous and you shape some kind of aperture within it. So having come up with this kind of approach, the first problem we came against was what are the limits on the achievable bandwidth if we use such a synthesis method. And the approach we used is based on causality, or also Foster's reactance theorem, which is a kind of circuit equivalent of the well-known Kramers-Kronig relationships in optics. And what we show in this equation, which is represented in this figure, is that the relative bandwidth, as we show on the vertical axis, is directly traded off with the aperture width, right? So the size of your metasurface, right? It's just a simple inverse relationship. And if you're doing some purely anomalous refraction, that trade-off gets worse for a larger refraction angle. So you see the yellow 70-degree case is more severe than the 30-degree case. And very qualitatively quite similar if we consider now a lens, all right, where we have again our operating bandwidth on the vertical axis and our aperture width on the horizontal axis. We see a very similar pardon me, very similar trade-off between the that gets worse as we have these cases here correspond to higher numerical apertures. Subsequently, a more formal, more general relationships similar to this were shown in this paper by Prasuti and Monticone. We've also shown that the thickness of the dielectric substrate and the permittivity also can limit the bandwidth, right? So this is a sort of extension to the above analysis. What we're showing here is the substrate thickness and the normalized bandwidth for different dielectrics, and we see that really the best case is to have no dielectric, right, or epsilon equals to 1, and to have a thickness of about 1/4 of a wavelength. That's kind of a known result, but it had not been applied to refracting structures, just to simple frequency selective surfaces. So here I'm now showing you one of the structures that we've demonstrated experimentally at millimetre waves. So this is the supercell of our broadband structure and a comparison narrowband structure. And my apologies for that background noise. All right, and this is the experimental setup where we have our sample Metasurface. This is at in the 80 gigahertz automotive radar band. So we've got this transmit and receive antennas. They are scanned around this sample. And what we're doing is we have some incident wave and we're measuring all the different diffraction orders that come from this structure. What we'd like to see, of course, is only one of those diffraction orders being selectively excited over a broad frequency range. And that's what we show here. If we take our broadband structure, you see our desired diffraction order 1, all right, is over about a bandwidth of 15 gigahertz. That's very strongly excited and all other modes are suppressed. If we consider the narrowband design, that's much less. It's only about 8 gigahertz. We've also done some designs at lower frequencies at around, so that was a reflective structure. This here is a transmissive structure, so it has the 3 different metallic layers. And we're now at X band, so there's 10 gigahertz. This was measured at ANU with by Ming Kai. And again, you see here we have the more conventional dipole layers on the outside, but the inner metallic layer, at least for some elements, is this inverse structure that gives us the parallel LC circuit. Here we're designing a lens with these given focal parameters. And this is a purely 2D experiment. Okay, and so what you see here is we're able to measure the full 2D electric field in this parallel plate waveguide. And what you see is over, from 8.5 to 9.5 gigahertz, our achromatic structure maintains a reasonably stable beam shape, whereas the narrowband one is really quite a mess and much less consistent. We also show some sort of 2D cuts in the desired focal plane. So that's what's shown here of the transverse profile. So you see a lot more variation in this narrowband design. The fact that the structure is worse is to do with actually our achromatic designs are a little more robust to being chopped in half to fit inside a parallel plate waveguide. Another more recent work that we've looked at is the angular response of such structures. It's all very well to design some kind of lens for normal incidence, but in many cases, the beam may not be normally incident on the structure. So what we're showing here, all right, is the focal properties of a lens. So again, this is in the 10 gigahertz range. This is in free space now, no longer in the parallel plate waveguide. So at normal incidence, as we go off axis, we see some, as we change frequency, of course, there is some degradation. But as soon as we go, to this 30 degrees incident angle, suddenly there's a significant suppression of this focal point. And we haven't solved this in this work, but what we've done is we've shown the origin of this effect. And what it all comes down to is higher order modes of these supported in the metallic layers. Because as you can probably see, to achieve our broadband response, we actually need to use relatively large elements within each unit cell. All right, so you may recall the narrowband type of dog bones were much thinner and less prone to this kind of effect. But when we have these thick, these very large elements that we need to get the broadband response, what we end up with is supporting not just the electric dipole mode, right? That's the mode that everyone's trying to use. That's what is predicted by and used by our model. But we also have here what you see, this kind of electric quadrupole type mode. And similarly, if we look in our inverse structure, we have, again, it's not a pure quadrupole, but we see this higher order variation. All right, and then the issue, what's shown in these two plots, right, where we're plotting the angle of incidence on the x-axis and the frequency on the vertical axis, all right, we see that while our desired mode might be relatively stable, this higher order quadrupole mode, at normal incidence, it's more or less impossible to excite. But as we go to higher and higher angles, you see that it starts to approach our desired operating frequency, and therefore greatly interferes with for example, the reflection phase at these larger angles. And we see a similar effect, or it's actually considerably worse for this inverse dog bone structure. So a multimodal model based on these higher order modes, it does agree quite well. It really predicts this observed behavior, but we admit that really solving this problem and controlling these higher order modes is still something that remains to be solved. So with that, I'd just like to conclude that similar to photonics, which has perhaps achieved most of the attention in this field, for microwave and millimetre wave applications require broadband and/or achromatic metasurfaces. We've developed synthesis methods that can achieve such broadband structures, that are practical for fabrication. We note that achromatic operation can create very severe limits on the aperture size, but if we give up on that achromatic behavior, then we have essentially no limit. But this excitation of higher order modes really needs to be controlled to optimize angular performance. So with that, I'd like to thank you all for your attention.
Okay, thank you, David. Okay, do we have any questions for David? I was just wondering what informs the choice. I love the name.